Hello, I'm Rodrigo Obando, and my presentation is titled Disposable Visualizations with Mathematica. Hello, my name is Rodrigo Obando. Thank you for coming to my talk. Um, I realize that a lot of the things that you see in the other talks is about, depth in Mathematica or in Wolfram language. That's not what my intention here. And also realize that the ultimate intention of what I'm actually trying to do is to promote Mathematica, which I don't think I need to do that here, because most of you, I assume, are users of Mathematica. But nonetheless, I wanted to trace back and before I came to Mathematica, and then now that I'm in Mathematica, and this is an idea that I've been having for a while now about the disposable visualizations. So there's the abstract, which is, not to read, but let me see if I can make this one a little bit bigger. Is it 200? No, too big. I think 150 might be better. Okay, so the idea with what I wanted to trace is that we sometimes, we try to make sense of the world, and we do that through our eyes, well, senses, and we try to do many things with this and try to acquire knowledge about our world. And we use some of the things that we use a lot. I know that not everybody, but many actually use visualization. We use that visualization so that we can understand what's going on in a system. And most of the time, that visualization is really the main target is yourself, is the creator of the visualization. And sometimes, some other people may actually understand or get about the same idea with this. Now, when we use the visualizations and we create all this, we gain insight. And then to me, that's the whole purpose of visualization, is that you are able to gain insight on whatever is underlying in the system. So what happens, though, is that when you create a visualization, you realize that you want to show that to other people. And this has been, something you want others to actually be able to do that and to understand the same thing that you understand. But sometimes we do not connect at the same level, and we end up moving ourselves away from our area of research into the area of creating visualizations. And now we shift, and then instead of continuing working on whatever we are interested in, we're now working in the visualization and trying to make it better and better so that others will understand, which actually moves us away from what we are supposed to be doing. So I thought that instead of doing that, we should not feel compelled to create these visualizations if the only purpose is to understand a system of a process. We should not be making better and better for others. We should make them better so that we understand, so that then later on we can use that knowledge to really perform something in our systems. So those are the visualizations that I call disposable visualizations. Now, I talked to somebody here that actually told me, they looked at me and said, disposable, it felt like bad. And what I tried to say was, it's not necessarily disposable, but it may be also called personal. So it is a visualization for me, and it speaks to me, and I might be able to see something in that, and maybe nobody else will. So it doesn't matter. I use it, and then I understand that. So these disposable visualizations, can be called personal visualizations, and they may be enhanced later on, and then other people might be able to understand. So how is it that I came to this? Well, let me give you some examples. At NASA, a long time ago, I was a graduate research assistant. I was implementing a fault-tolerant multi-computer operating system, for NASA Langley. And the implementation involved testing multiple computers, and they will be talking to each other. I wrote that in assembly language. And as I progressed in the implementation, I realized that I had no idea how these multiple computers were actually working. And I was supposed to be, doing all this, but I didn't know that. So I needed to visualize the overall system and not just a single computer. And what I did is I developed a simple log system that will report important events in the system, and I used visualization idea taken from digital analyzers. My undergraduate was in electronics engineering. So I looked at that and said, I'm going to develop something like that. I actually wrote it in QBasic. Anybody ever heard of that? Yeah, QBasic. I guess Bruce, he probably heard of that. The idea that I developed with that, this step was not really required, in terms of the whatever I was doing, but I needed it for me. I wanted to know that whatever I was doing was actually happening, and there was something going on inside. So I demonstrated the project to the research group, and I also showed the visualization tool as an added bonus. Contrary to what I'm proposing, that particular visualization was not a personal visualization. So in this talk, that's not the thing that I'm trying to do in this talk, but the tool was revealing to the principal investigators when they saw it. So in 5 minutes, in looking at the visualization of the events of the operating system, they realized that they were going in the wrong direction in the research. They have, they use transition matrices. They use actually Petri nets, if anybody knows about Petri nets. They use those matrices to analyze the system, primed, to what I joined the group, and then they looked at that and they said, well, I think this visualization is worth the time to invest. And I said, okay, so that became a complete part of the research. But that one hit a point with other people. But that was originally was just for me. It was just, actually one of the investigators called it the ticker tape, because it looked like stock. Now, later on, I was in business, and I was working for a corporation, and I developed all the software for daily operations. They did from billing and payroll and everything that they needed. I developed for them. So they printed long reports and weekly, about all their accounts payable. I know that this is probably boring for all of you, but the businesses need the money, so they printed all these invoices, and they were thick reports every week, and they were handling the accounts receivable one by one. So I came out with an idea. I said, this is terrible. And then it all comes to just a bunch of numbers. And I know that you're saying, why did I do that? But this is back in the 90s. So I developed a visualization of that I could not only visualize every client, every invoice, but I could say conglomerates of that and aggregations of that. And I could actually look at the entire health of the company by just looking at that visualization you see on the screen. I call it ring tuple because it's like a ring, but it was several rings, so it was a tuple. And it turned out to be at that time that it was sort of okay. So after I finished in this company, I got an invitation to go and teach, and I actually used it with students. Students sort of understood that. They got it. It can actually be used in many other things. And by the way, I wrote that in Java 3D. I doubt that any of you ever used Java 3D. It's actually a defunct product. It didn't last too long. But I used that. It took me a long time, to really make it work, etc. So I decided to take it to a visualization conference. And they looked at it. And they asked me if I had tested it with people. And I had done this and I done that. Then I realized that this was no longer personal. I needed to test it with many other people. So, and I said, oh my God, there's so much time that I used on this, because I had to work on this, and I had to do all the manipulations, etc. Even though the underlying system is a series of vectors, but I needed to do the 3D, which is the visualization. So that was not very good. Anyway, in cellular automata. So as I met, Stephen Wolfram, and I became interested in cellular automata, my first pass at it was actually using that visualization that I showed you before, I called ring tuple. And I started doing all these things, and in reality, I started looking at how the cellular automata is working and how they, I tried to understand that because I didn't know that. I even presented a poster in one of the conferences. So I was on a train to New York City when it actually hit me, and I was able to do, to see the visualization. I said, maybe this is a way to do that. Now, this is a visualization that nobody has seen. I mean, most people have not seen. This is the visualization that I did when I was in the train. And to me, it spoke tones. It was a lot of stuff I was saying. What you see in there is there are 8 different points, and each one of those 8 different points is one of the states of the 3 bits that are defined in the cellular automata. You have the central cell and the 2 on the. So if you have that, that's 8 points. The ones on the top are the ones that the central cell is 1. The ones on the bottom, they are 0. Now, I did this just as a matter of understanding. I wanted to have a better idea of how that was working. So I created it, I wrote it in Mathematica. And then, of course, with a line of code, I was able to then just do all 256. And they are actually ordered in a way that, that this particular visualization allowed me to look into this. And then I wrote a paper in the complex systems in a different way of looking at the cellular automata rules that allows me to do this kind of ordering so that I could see it in here. And then I started to see certain areas within the space, but this was one line of code at the end. So it became to me something that I can just dispose of, that was personal, and I didn't have to make it so that other people will have to see it. So I continue, working with something like that, and I was interested in the local Markov change of this, and then I used again the 3 bits, and then I had 8 states, similar to what you had before, and this is the entire space. Well, I cannot see it all of it, but you can see that there are areas in here. Let me see if I could.
What does a link mean in this case?
The what?
What does a link mean in this case?
Oh, the link is the probability of jumping from one state to another. These are Markov chains. So the interesting thing for me was that if you see here right in the middle, you see how these rules are similar to each other. So the ordering of the rules was actually appropriate for these. They actually show, side by side. Or look at these other rules over here. They are similar in terms of their local Markov chain.
Which one's 30?
30 is right here. And 86 is down here. Which is, if you see it, there's just there's a manipulation of that, it's a rotation. And then you see it, this is symmetrical across, and then you see it over here, the same thing. And then symmetrical over here, this is 110, and this is the 124, which is part of the same class, and this one over here is the other one, 193 and 137. And you can see that, you can see certain things, certain characteristics of that. So look at this one over here. It's almost like this one, except that there is just an anomaly that made it class 3, made it completely go random. So I started looking at all these things, again, very personal, but this allowed me to, again, in one line, after I just wrote the little visualization of the cellular automata, to be able to see the entire set. So the interesting thing with this is, as a spin-off of this, I actually came across another problem. That's a math problem, which is this is the one. Yes, it has to do with monotone Boolean functions. If anybody knows about monotone Boolean functions, they are actually very special functions for certain things. They're actually the number of monotone Boolean functions giving a number of variables is the dedicated numbers. So it's 2, 3, 6, 20, 168, 7,581, etc. So I became interested in that for reasons that I saw in there. I started investigating into something like that. And let me show you something that I quickly did with that. When I did that, I actually presented this here in 2006. And then I in fact, because of the visualization, I saw that there was an interesting way that the lattices will go from one to another. This is part of the sequence. And the way that this is computed is very involved. We have only computed 8 numbers, but I was able to find a way to go from one lattice to the next one directly. And as I said, this was a spin-off of the work that I was doing. So it allowed me to move into other areas just with a simple visualization. And I actually I created a subdirect product for those of you that know about subdirect products of lattices. So going beyond all that, 2 years ago for the student, I also came out with a probabilistic cellular automata that has all kinds of interesting characteristics. And now I'm also, let me see, I'm working something that I presented last year, which was an exploration of the spaces. And let me show you something real quick in here, like something like this, that I can go into not only the ECA, which is the elementary cellular automata, 256. This is actually mapping inside the bigger space, the 4 billion rule space. And then I can take a little piece of that. This is 124, 110, but this is mapped to the higher, into the higher space. And I can see in the neighbors, there are many of those that look similar. Now, this is something that I have not seen anybody else doing this kind of mapping. So I was able to do something like that. And what am I? Here. So I've demonstrated all those things. Those are available on the website, etc. So in conclusion, and I wanted to show a little bit more, but I was robbed of a little bit of time at the beginning. So, but if you use visualizations of any kind, you should not despair if others do not understand what you are actually trying to show. It happens to me a lot. Perhaps those visualizations are just for you, personal or disposable, or as a colleague I met during this conference called it ephemeral. And so we make models that what we see around us in order to understand the world. So let us create a myriad of visualizations that will help us unveil the mysteries of the world. Remember, your visualizations may just be scaffolding for discovery. And that's what I wanted to show. And I think I have time for questions, right? Yes?
Could you go back to your rule embedding with a rule description in terms of the colors?
Yes.
I didn't quite catch what the colors meant. And
Oh, yes, yes.
I was seeing it as a three-dimensional shape. Is that what it is, or is it just triangles?
Let me see. What was that one? Oh, yeah, that one. Sorry. This one.
Yeah. No. So yeah, I didn't quite understand. Am I seeing this as a three-dimensional figure, or is it a?
They are three-dimensional. They are. This one. This is Rule 30.
Okay. So
All right.
There are two levels. There's like a top plane and a bottom plane.
Correct. Yes.
Okay, and then each of the triangles.
They actually show transition.
They're all right triangles, right?
Yes. So this is the way. This over here are 0. They are the central cell is 0. When it's blue, it is actually transitioning to 1. When they are red, they transition. They stay in 0.
Okay, so now this is a plot basically of the central.
Yes.
Okay.
Yes. But see, again, that's what helped me understand. And actually, this drove the paper that I published later on, where I decompose the rule into two primitives, primitive 0, primitive 1. And this is extensible to any other, if we have mod 3, I have 3 primitives. And the interesting thing is that, for instance, if you look at all the Boolean functions of the ECA, 256, I can show those and generate them with Mathematica using only 16 of those. Because all those 16s is how actually expresses every one of the two primitives. So if I do a product of them, I can actually generate 256. So that was the basic idea, but it moves into the other states as well. It moves into color, 3 colors, 4 colors, etc. You always have the number of colors dictates the number of primitives. Yes.
Have you tried to use feature space a lot for getting clusters of different objects?
My student a couple years ago, this is what we did. No, this one. This is what we did, and then he discovered, for instance, when he actually did that in terms of feature, not necessarily in the rule, but he found that those 8, they are related. They're not the same class, but they are related, as you can see, and there is a complement of those. In fact, the signatures of these clusters, is what dictate this, and that's what allows us to do probabilistic cellular automata. Which actually combines the features of all those into one. And unfortunately, I don't have it here, but 2 days ago on Wednesday, I was showing in the HoloLens, because I have this in 3D, that you can actually go in and see that, and then you can see the different clusters and how those generate the probabilistic cellular automata and the evolution for that. He actually used, sometimes analyze using the image, using fast Fourier transform for comparisons. Some other times, you just did a brute force. We were just exploring the space. Now, if you look at the space, they are joined by there is a distance. It is a difference of 1 bit in between each one of those. And that's how he was able to navigate, one at a time. So he wouldn't just go into the entire space, because there is an order, and there's in fact a lattice in, I think, 4 dimensions. But yeah, we look at some of those things. All right, thank you very much.